We're Team 6, and we did an underwater robot for our competition. We designed a brochure in multiple languages, which we'll be handing around, so you can pass around. It's full of global learning aspect of our project. It's a brief description as well as the controls of what our robot uses. This passes around in the 2 languages. There's 5 languages: Turkish, Persian, Italian, English, and Spanish.
I'll take Italian.
Alright, so like Nico said, I'm Brandon, this is Josh.
Hi, Nico.
And we're going to talk to you about the underwater research and scientific apparatus. The first thing is, we're going to enter the MATE ROV competition. We have to design and build an underwater ROV. It has to be capable of research in oil pipe maintenance. That's like more of a concept. What we're really doing is we're going to go into a PVC cage with garbage bags on the outside to try to pick up like PVC type objects, stuff like that. The most important thing that we're going to do is keep it cheap, because it's us 3 paying for it, and keep it small. We're going to go for the Ranger class. It's called Science Under the Ice. And like I said before, just oil field production and maintenance and deep sea pipelines. The first thing we did was we looked at some previous examples of things. The top right here is a more modern and commercialized version of it. It's got like the ducted jets and everything, much more expensive. The Purdue one down there is the class above ours. That's a team of 10, 20, 30 people with multiple $10,000, $20,000 budgets. You can see they opted for the 4-fan design just to get it to rotate. Then they've got fans to get it forward and backwards, whereas we have 4 in total.
All right, I'm going to walk you through some of the standards here entailed within the competition, which you are basically forced to abide, obviously, right, for safety reasons, and you want to keep everyone within the same page and competition level. These are some of the standards instilled by MATE themselves with some of the partnering companies that establish these standards, like ANSI and such forth. And most of them have to do with you can't use hydraulic fluid, or if you do, you have to take a test proving that you have knowledge on this, lasers, and such forth. For the most part, the standards that we really cared about was this IP rating. And the IP rating is the ingress protection rating. And basically what these 2 numbers tell you is the first number is going to tell you how much can the enclosure withstand as far as the particles, dust, any sort of small granulated substance that could enter. And what the second number is going to tell you is how waterproof it is. In our case, I'm not sure if you can see well from there, actually the water numbers range from 1 to 8, but we're really more concerned with the numbers ranging from 6 to 8, because 6 is where the water level protection begins, that it's called water resistant. So you can assume that you hit it with a hose and water's not going to get in. 7 is you can submerge it for a short period of time, up to about 3 meters of water, I believe. And so obviously not long periods of time. The goal is to reach an IP6-8 rating, where 8 tells us that you can submerge it for a long period of time, it can sustain a lot of pressure, and it could be under multiple depths of the water. This is the finalized concept of our design. As you can see, we're the shrouds are kind of missing, and we've added a little bit more. But for the most part, everything's there. The shrouds would be mainly for the safety and for the safety of the environment if we were operating this in underwater in the ocean or something. For the overall construction of the design, we went with a open design to try and increase the water flow to give us the least amount of drag force. We did this using PVC. We basically put all the PVC together using PVC cement. For the box, for the most part, it was watertight with, so it's already a water-resistant box. We sought out to further improve that by sealing it with some epoxy. We also had to create holes for the wires to flow through, as you can see illustrated in these pictures here. And what we basically did is we cut those holes, put some epoxy on the ring, slip this through, and filled up the entire ring itself with a marine sealant. Oh, and to add, all the metal contacts are also have Loctite on them, so that from the vibrations, these things don't come loose.
Here we have some alternative designs. These are the 2 original designs we came up with. This is the one that was on our poster board, which is the design we were opting for. But because it had 4 propellers on top and 2 in the back, it was much more expensive to have more motors and propellers. The propellers themselves are very expensive. So we opted in for a different design, and from there we realized it was even easier just to make a flow-through frame, and then we built onto our current design. The original one had a center console, same way as our current design does, but it was circular, since the sphere is a better flow-through design. Here we have some of the simulations that we've done. The first one is for drag, and for the flow of the water, we used the standard equation for drag force, which we equated using SolidWorks. We used to simulate the force in the x direction, and by the robot moving at 20 miles per hour through the water, which we got the force from there, and we put the average force into this equation to solve for the coefficient of drag, which is approximately 0.11, which we feel is pretty good, but obviously the real one, since it's full, it's going to be a lot higher. Here we have two different views of the drag, the side view and the top view, to demonstrate how it flows through the water. Here we did a simulation of the forces that would be experienced by the motors. The motors are advertised to produce approximately 1,000 grams of thrust, which I averaged to about 5 pounds maximum of force, which is obviously more than they're actually going to experience. So if our frame can withstand that, PVC is very sturdy. We obviously knew it would succeed. So with the fixed on the bottom and the 5-pound force on top, we experienced, next slide, that's how we simulated the force. And from there, we were able to witness the max stress of 620 psi in the joints in between each of the connectors, around the holes particularly. The strain was the maximum value of 0.001. Next. And you can see the result displacement, which is 0.013 inches, which is insignificant. And the factor of safety was, the minimum factor of safety was around 13, which is enough, we felt.
All right, so the first thing is our main component design. We started up with an Arduino, and from there we're running an Xbox controller wirelessly to the computer, and the computer's tethered to the ROV itself. We have the 4 brushless DC motors, 2 on top, 2 on the back. And if you want to go forward, both of them go forward. And if you want to turn, if you want to turn left, the right motor goes forward, the left motor goes back. Also, we're using the GoPro Hero 3 as our camera. For propulsion, like I said, we have that. We have our electronic speed controls. They reverse and forward, so you can dive, and surface at the same, well, not the same time, but same area. We have our Mark II robotic claw. It goes left and right like that, pans, and it opens and closes the grip plates. Here's our prototype. This was maybe about a month or 2 ago. And you can see our LEDs on the front, and that's when we had the zip ties holding our box in place, and everything was great. This worked pretty good. Our main issues were our speed controls that we had did not reverse. We didn't know that because it said they're forward reverse, but they said programmable. That meant that we can go through and program it so it can go forward or reverse, not forward and reverse. So after testing in the water, go forward and down. That was fine. It was great. It worked. Our waterproofing worked pretty well. We had no major issues. But then we replaced everything with the larger forward reverse speed controls, and we had quite a different design, as you can see here. The main thing is that they're much larger, and the box doesn't quite close fully. And when you have an underwater box, that's very important. So we used some JB weld, like this water weld, around the seams of it to try to get it to fully, waterproof it. Didn't quite work. Came close, but it had a little hole. So we tried it again. Then we used this rubber type spray around it, and we were still getting water because we're basically trying to seal up like a big, gap around the entire thing. So eventually, we were just like, we want to get some more out of this than just what we did forward and down. So we decided to foam the whole box in and around it, and it worked great. It's waterproof. The problem is now the foam, lifts the whole ROV up a lot. So that's why we have to add weights. We had to add even more weight than we thought. So our main thing would be to go back to the speed control dimensions we had before, but have ones without fans on them and just try to find some smaller ones. But at this point, when we got all the new ones finally, we only had like a week or 2 to go, and it was taking a long time. So it does work. It doesn't look that pretty, but it works great. This is a quick view of our command center, I guess. We got the computer, the Xbox controller, and the ROV on the tether. Oh, this is us testing it a little bit. It's kind of hard to see, but it actually is fairly neutrally buoyant. It has a slight positive, so we'll return.
That's the first person view of the robot.
It's basically what you would see if we had this sort of a connection tethered to the computer where we were controlling it for the competition. This is the window you would experience.
You can see it kind of like, diving, surfacing, depending on which button we press. Also, the motors they range speed from about 90 to 180. It's interpreted as like a servo command given to Arduino. We're running at about 110, and it still moves pretty quickly. At about 160 to 170, the weight slow it down a lot, and things get a little crazy. Another issue we have is you see the lights. They dim a bit because on the surface of the water, the lights don't dim because the current is not that high. But as soon as you put the propellers in the water, the current's much higher, and the draw is much more, so it dims the lights on the LEDs.
It's moving much faster than it looks like. You can see the labels filling really quickly, just that the image doesn't take the picture.
I think it's the refresh rate of the camera.
Yeah. No, it continues. It's like a 2-minute video. This is different maneuvering, as you see through the water. Pretty much, you see it gets closer to the pictures of the camera, and different views, so you can see exactly what we're doing. Testing it for.
If you'll notice, the lights seem to either turn off or dim depending on what motor commands we give, and that has to do obviously with the power draws we were saying before. Just depending on whether we're going forward or up. Typically, the forward turns them out, I believe, and the upward dims them, and that's because it has to work not as hard to push it forward. I mean, I'm sorry, to lift it as it does to push it forward.
And then 2 videos of the claw.
See the claw opening, closing. It's got like a pan, and then you can open and close it based on the triggers of the remote. And then there's a button to center it, open it, so it's ready for the next one.
And the left is the underwater view at the same time as everyone's supposed to be playing, but it wasn't on that.
Oh, and our underwater camera is also the same camera that we use for the first-person view. That's why you don't get both at the same time. There you go.
Right, so this was the Gantt chart that we followed for the overall project itself. This was the timeline that we used to keep us on track and basically, basically kind of keep us in line as to how much progress we're making with the time lot that we have.
So here we have the global design. As you all saw, you passed around the pamphlet in front of you. Our main focus of the global design was those translated brochures, so that way everyone who reads it would be able to actually understand and see what we did. They'd be able to change the controls if they so desired. Even explain what programs we used for the ROV. We wanted to include also the environmental conditions of what it can function under. Brushless motors can work in salt water as long as you clean them after usage, otherwise they will segregate. Also, it's battery powered at the moment, which means that you can pretty much use it anywhere. You don't need to plug it into the wall and convert it over. Some concluding remarks. Our final steps to do is to fine tune the system. It's stronger than it needs to be, so we can make it even smaller, even thinner material, so it costs less. And the marketability. If we would ever go to market with this, our obvious selling point would be that it's small and affordable compared to the available things in the market right now. Any questions?
Yeah, so what's the reason for that? I mean, is that a competition or is that?
Yeah, the main ROV competition.
Yes, sir.
And you have parameters that they set?
Yeah,
You do that now?
Size and
You did all those drag tests and everything with nothing in the middle, so is that because it was before you changed the design on it or something?
Yeah.
It worked originally with the original speed controls we had, but since we changed the design and the waterproofing had mistakes, we had to do that to prevent it from damaging all the internal circuitry.
Yeah, I mean, the stress test and all that is fine.
Yeah,
That's
we
a
did
it
good
just to
idea
frame.
to do it without anything.
Right.
Now, the test is gonna be on a freshwater pool?
Yeah.
Yes.
But we did research and made sure, literature that it would actually work in salt water. Just you have to take care
Or
of
it'll
the
be more
motors.
buoyant, so you'll be
That's true.
even worse off if it's a little positive right now, that's what I was asking, so.
I did a test of buoyancy also of the frame. What I did was we put into the tub and we did a volumetric displacement and we got the density of the water as well. And we compared that to the actual weight of the ROV and it was slightly positive. So it's supposed to be slightly positive so it can resurface naturally if it fails. But when we added the foam, we added all the things, it did change all of our study's original design and it was too late to probably go back and change everything at that
So,
point.
and are you guys divers?
This guy.
So, you know, about the BC and all that, so.
Yeah. Yeah, actually, some of the weights on there are for my dive boat.
On the matter of the fluctuation of the battery power, as it manifests itself in the lighting, what are you doing to fix it?
I think we're just gonna run 2 batteries.
Yeah,
Just strap them together, and it should still maintain the same, higher max amperage before it starts doing.
Did I see an economic breakdown, financial breakdown of?
I don't think we have a slide on it, but we can tell you about it right now.
We have the total cost in one of the slides. If you go, it's $1,200 was the total estimated cost, including all the Loctite, all the like everything we had to put on the robot was included in that, not including the weights that we added on now. But we got donated a lot of the things. The PVC was sponsored by, what's the name?
Stern Brothers Plumbing.
That's why we painted it pink as well. Their company is pink. We painted pink in their honor.
Oh, you know, I always see this in all the designs here, they never include labor cost. You know, I know you guys are free, but that adds to the cost.
Yeah, Professor Zuccarelli actually machined out our propellers. They weren't originally threaded, and he threaded them for us, and they fit perfectly. So that was included in the cost, actually.
It was.
Just because that's the only thing we machined was by him, was that one thing. We did everything else ourselves. That's not included in the labor. But besides that, that's the total cost. We actually get around $600 because we got a lot of donated parts. The GoPro is $300, and that was donated by his cousin, which saved a lot. Arduino was donated by a fellow student. So a lot of the things were chopped off the price.
Yeah, I see that, but I'm still thinking you should actually put the real
Make it
cost in
real,
there.
make it
You
real.
know?
$1,200 is the actual total cost. And
Or
we didn't-
1,200 is what you
Yeah,
said.
we didn't include the table, though. That's our mistake.
There's one thing that's your cost, and another thing is the actual cost, if you didn't have freebies
Yes.
and all that.
Yeah, 600 was the price of after donations, and before was 1,200. We're actually relatively cheap compared to the competition, what everyone else is.
I mean,
We use brushless motors.
Yeah, like 12, 10 grand. Or something.
When you go to market, those costs become a real
Oh,
factor.
absolutely. Well, that was, I think the bigger picture I was looking at too was from both the global and the economic aspect. Really, realistically, going back to the parameters of the competition, it's to perform a certain activity. It's for a long-term goal. I think I would have liked to have seen a little bit more of the financial global impact from that goal. So yes, here we're designing an underwater robot for $1,200, but it's underwater pipe repair and maintenance. What's the potential impact and benefit of it?
Now, also you, in the presentation, you alluded to the environment. Could you talk more about the environmental impact that it's going to have?
Say a little bit. Well, the main point is to not have to send people down and to, kind of help with hazardous areas around piping and stuff like that. There's not like too much, we're only entering the competition. It's the theoretically what this is for to help the environment.
Exactly.
Now, we're not specifically helping the environment too much.
No, but I'm
it's
thinking,
proof of
how
concept.
is that gonna repair anything? I mean, I understand the visual inspection and stuff, I understand the competition aspects of it, okay? But to repair a pipe,
Oh,
and
no.
one claw, I
Well,
think,
yeah, there would be,
No, they have to.
you need several of those.
The competition itself
It's titled that way.
is said it's for that purpose, but they don't actually, it's supposed to be underwater ice conditioned to maintenance the pipeline. It says to deliver a Christmas tree, is what they call it, through the pipe, and to tie in you have to tie in a thing, you have to do that, the valve. But itself, they don't actually do anything with the pipeline. It's just that's the parameters they set. And when they actually go to the competition, you can see other people doing it. They just move around pipes underwater. They move around like little PVC. They need you to be able to
Yeah,
gather
it's a
some
test
samples, so
thing.
they can take a picture or something.
Yeah.
Because it's
You're
a
not putting a
small
pig in
scale.
the pipe or anything like that.
If you win the competition, they sponsor you to go to the next level is why.
Right.
And then you take your design and you increase it from there to the appropriate levels actually to do the maintenance of the pipelines.
Okay.
This is just like a conceptual idea.
Actually, I think it's called a pig, you put it aside.
When is the competition?
I believe it's actually coming up, it's next 2 months.
It's set on your timeline April, are you entering it?
Yeah, we're gonna enter. It's not for, till after you graduate.
I'm sorry, the timeline is, the registration is now in April, but the actual the actual competition is broken up into two parts where you compete here in Florida regionally, and if you qualify there, then you go to the international level where you compete with everyone from across the globe. I mean, universities, both here and across
Canada,
the
mostly Canada. A lot of it's in Canada.
That's it. Any other comments? Aaron? Thank you very much.